consider the space B of n, which is collection of all maps from n to n, all maps which are bounded linear maps. Rather, I would rub it. The word is one word, linear maps are continuous linear operators. If continuous linear operators from n to n. So the all continuously they are called as one word as operators on n. So what we are going to talk is the conjugate of an operator. The symbol. So you have this space Bn. Okay. So T is the map here. So T is a map from n to n. T is given to be linear. T is given to be continuous. Okay. It's a bounded linear map. So what we are going to define the conjugate as T star. Okay. So it would be called as the conjugate of T. It's an operator. It's an operator. So T star also would belong to a B of n. It would be T star would also be a map from n to n. T star would be linear and continuous. So let's try to define this thing and let's look at this thing. So what do we mean by this thing? So we consider the Helm space. So let n be norm linear space. So we consider the space Helm of n to f. If you are familiar with what is Helm, so this is nothing but, let's call this space as maybe say L. So L is nothing but all scalar valued linear maps from n to f. Okay. So this is L. So we have noted that we are just having linearity, okay, and we are not having continuity. Okay. We are just focusing on linearity. We also know what is n star. So B of n to f. B of n to f is denoted by n star. So this is what? This is the linear maps, scalar valued and continuous. Clearly n star, so one can easily see that L is a vector space over F. So if you take any two maps in here, maybe say F and G belonging to L, what does that mean is that F is a map from N to F, G is a map from N to F, F is given to be what? Linear. G is also given to be what? Linear, right? F is linear, G is linear, so F plus G is there. So how to define F plus G? So pointwise addition, F plus G of X would be what? F of X plus G of X, and pointwise addition and the scalar multiplication. So if alpha is element belonging to F scalar, then alpha F on X would be alpha multiplied by Fx. Okay. So this way, this becomes what? If we, and we can apply maybe say the test for. So F plus G is there. This is scalar. All the conditions, eighth condition of this thing are easy to check that it is indeed satisfied. So L is a vector space over F. Since n star is also vector space. It is B of n comma f is a vector space. So what do we get is that L is there, n star is there. So n star is, this is a linear and continuous. So is a subspace of L. So n star is a subspace of L. Okay. Now let's look at operator. Okay. So operators we have seen. So what is an operator? So this space B of n. So it's a space of all linear, continuous maps from n to n. Okay. Just like L, what we can look at here is that just look at linear maps from n to n. So let's call that space as maybe say so L tilde is collection of all maps. Let's say T will use from n to n, which are just T is what map? Linear map. One can easily see that L tilde is also vector space. Otherwise, the point-wise addition and so on. So if you take maybe say T1 and T2 belonging to L tilde, then so T1 plus T2 of x would be what? T1 of x plus T2 of x, and this is again in n, because n is again what? Non-linear space, so you have addition and so on. So L tilde is in fact what? So this is L tilde is a vector space over F. Not only that this is a vector space over F, but we can also claim what? We can claim that easily to see that B of n is a subspace of what? Subspace of L tilde. So we consider this L tilde all maps TB the map from n to n and T linear. T dash, where so L tilde is T is a map from n to n, T is a linear operator, T gives rise to the object T dash. T dash is an of mapping from L to L. What is L? L is collection of all scalar wide linear maps. Collection of all maps from n to f such that f belongs to f is given here. F is linear. This kind of a thing. So T dash takes a scalar valued linear operator and produces a linear operator. So that is what we want to define T dash. How does that T dash is there? So let's see that. So T dash is acting on objects of L to produce an object in L. T dash of F would be again a map from n to f, which would be linear. Because if it is a map, so we need to define on the points on the n. So T dash of f acting on x, x is in n, we define as the following: f of t of x. What is t? T is linear map from n to n. So tx is an object in n. So this is object in n, and f is a mapping from where? N to f. So it's again, so it's really indeed a it's a scalar value. So t dash of x. it's easy to see that T dash of f plus g would be what? On x would be nothing but, by the definition, would be uh, f plus g of tx. That would be f of pointwise f of tx plus g of tx, and that would be T dash of f here. It would be T dash g of x. This is nothing but T dash of f plus T dash of g acting on x. So that gives that T dash of f plus g is indeed, this is true for all x belonging to n. This operator is the same thing, this map is the same thing as T dash of f plus T dash of g. And similarly, if we have alpha f, we can write here alpha f and it would go this way. Okay. So T dash is indeed a linear map from L to L. If we focus T belonging to B of n, which is a subset of this L tilde, even if that, so what do we have? T is a map from n to n, which is L tilde. T dash is a function from L to L. So it takes a map, a scalar valued linear map to another scalar valued linear map. So T dash, so L is what? Linear, n star is continuous. So T dash, even if you restrict our domain, under what condition we will have that this L could be, so when so conditions as when range can be restricted. So T is in fact here itself is a map from n to n. Okay. Well, and what kind of maps these are? These are linear and continuous, and this is just the space of T, or this which is there, which is just linear maps. Okay. So let's try to see how do we get it. Let's observe the following situation. Let S be closed unit sphere. S be closed unit sphere in N S is collection of all those x belonging to N, such that norm of x is what? Less than equal to 1. Then P is continuous for the characterization of continuity. If P is continuous, if and only if what happens? P of S is a bounded set, the 4 equivalent criteria. This is if and only if what happens? F of T of S, by the theorem following what the uniform boundedness theorem, f of T of S, so x is bounded in N if and only if f of x is bounded for each f, is bounded for each f in n star, sorry, which is if and only the t dash of f, this is f of t of x, the definition of this thing, is bounded for each f in n star. So if this is bounded, again one more we can apply over here, from here over here, is that this is a set now on which it is acting, non-empty set. So it is if and only, again, the t dash of f is what kind of a set? Is bounded for each f in n star. So what does that mean? The continuity of t. So t is continuous if and only if what? T is bounded. So t is just a linear map from n to n. If we are making it continuous, if and only if ts is bounded, if and only if f of t of s. This is the theorem following the uniform boundedness theorem, or the Banach-Stein's theorem, the corollary you can call it as that, the following theorem. This is bounded, this by definition is this thing, but this is itself a map, and then this is a set. For each this is happening, then this is bounded. So what do we have? Characterization is that so t dash would be in n star, would be contained in n star if and only if, so t dash of n star would be contained in n star if and only if what happens is that t is continuous. T is continuous. And in other words, if we restrict, so T was just a map from n to n, and it was just a linear map. And if we restrict it to continuity, then we are getting the T dash of n star is n star. So T dash, if restricted to Bn, T dash, if restricted to Bn, would produce what? So T dash acting. Okay. So T dash is acting on maps which are, so T dash of f, so rather it would be abuse of notation. So what we'll do is that, so since T dash of f, this acting on x is f of t of x. Okay, this is the case, and then t is in n, and t is the linear map from n to n. So if we rather focusing on d of n, then what we get is that t dash of n star would be contained in n star. This is what we have. So then in this case particular, we call this t dash by the name t star, and t star of n star would be contained in n star. So t star is acting, so t star is in fact a mapping from n star to so n star to n star, and the definition would be as the following. So t star of f on x is nothing but f of t of x, where t belongs to b of n, or t is a map from n to n, which is linear as well as continuous. F is the object in n star, which is b of n to f. Okay, so f is a map which is linear as well as continuous. So this is the way how the conjugate is produced. So let's look at the norm of T star of f. The linearity of T dash is already seen. So what do we have? The norm of T star would be the following. It would be T dash of f. It would be the supremum of norm of T star of f such that norm of f, this is the supremum norm, less than equal to 1. So f is so T dash is a map from n star to n star, so it's acting on the functions. So we have this kind of situation. But itself here, this is T star of f, we have the supremum norm here, right? So what do we get is that we'll write this as it is, and the definition of this one, it would be supremum of norm of T star of f acting on x, okay, such that norm of x is less than equal to 1, and such that this condition as is norm of f, the sup norm, less than equal to 1. So these two, supremum and again supremum, we are taking, so we can write this thing as supremum over a norm of T star of f on x such that norm of f less than equal to 1, norm of x less than equal to 1. So these two things we have, x and f. So what do we get from here is that by the definition, T star of f on x is the supremum of norm of f of t of x, and then such that norm of f is less than equal to 1, norm of x less than equal to 1. So f of t of x. Okay. The point is that f of t of x is an object in n. It would be what? It could be written over here as so this is less than equal to this sup as it is norm of f times norm of tx, right, less than equal to, so such that norm of this is the sup norm less than equal to 1, norm of x less than equal to 1. But norm of tx is again what, less than equal to norm t times norm x. So this is supremum of norm f, norm t, norm x, the sup norm less than equal to 1, norm x less than equal to 1. So what do we get from here is that this is less than equal to 1, this is less than equal to 1, if you put here, and this is supremum over f, you look at here, over f and x, so this is not less than equal to norm of t. So the left hand side was norm of t star. So what do we get is that norm of t star is less than equal to norm of t. This is the first condition. In fact, the converse is also true. And why is that case? Is that because f is the theorem following Hanbanach theorem. So if you take T, map from n to n, linear and continuous, suppose and take any x belonging to n such that Tx is non-zero. If T is not identically zero operator, then we can have, certainly there exists a x, Tx is non-zero. So there exists a functional n star. So Tx is an object again in n and non-zero. So functional such that norm of f is equal to 1 and f of then at this point, if you call this point, so f of t of x would be equal to what? Norm of t of x. Okay. So if we consider this thing, what will happen is that in the definition of t star of f, this f is 1, and definition of t star itself, this is equal to what? The supremum of norm of t star of f such that norm of f less than equal to 1. So there is a f whose norm is less than equal to 1, and then in this definition, if you take this is the double supremum, as we have seen, supremum of t star of f of x. So t star, so f of t of x, in that case the third statement. So this is the same thing as we had observed. Let's write that maybe. So this was the same thing as the supremum of norm of f of t of x, such that what happens, norm of f less than equal to 1 and norm of x less than equal to 1. So what do we get is that this is indeed from here this would be that this is over all those f, these and x is there. So there is a f on t of x is norm of t of x. So it is all the value of norm of t of x it is taking, and then it is supremum. In other words, norm of t, from here we can directly claim that norm of t is less than equal to norm of t star by using this fact, and then hence what we have is that both the cases are established, and then we have that norm of t star conjugate operator is indeed the norm of t. Okay. Some properties of this thing: if alpha and beta are scalars, then alpha t1 plus beta t2, its star is what? Its star would be, if you want to look at, so on f, t star of f, so it would be, if you are considering t star of f, if you are doing on x, it would be f of alpha of t1 plus beta t2 on x, which is nothing but f is a linear map, so alpha ft1x plus beta ft2x. So what happens is that this is alpha t1 star of f on x plus beta t2 star x. So we have that. What is directly from what we can claim from here is the following. This is alpha t1 star plus beta t2 star. Okay, this is the case for alpha beta scalar t1 t2 and the conjugate in this one. Similarly, what would be I star? I star is easily seen to be as I. I is the identity operator. T1 T2 star, however, is, this is the claim, T2 star T1 star. And why this is the thing is that because T1 T2 star of f of x is what, rather not this f of x, on f, and then we have over f, and this over x is what f of t1 t2 x, which is f of t1 of t2 of x, which is nothing but t2 star of this one, t1 of this thing and so on, is t1 star of f on x. Okay. So what does this give? So this is true for all x in n. So we have that T1, T1, T2 star is T2 star, T1 star. So what we have proved is the following. If T is an operator on non-linear space, then its conjugate is T star. Is an operator on N star, and the mapping T going to T star is, because norm of T is the same thing as norm of T star, isometric isomorphism of Bn into Bn star, which reverses the product, which is T1 T2 star is T1 star and T2 star, and preserves the identity I star is the identity. This is what we have. That ends this discussion on Banach process.